Hello everyone, this is the fourth video for chapter 19. So in previous videos we talked about work and delta E thermal for PV diagrams. This video explores heat in PV diagrams. So also in previous sections we looked at heat for solids and liquids. This time we talk about heat for gases. And that's why we're not just talking about vertical lines on a PV diagram, but for gases the volume can change. So as we'll see in this video, this will complicate things a little bit. Also, one thing you should be aware of is that this video is sort of part one of two parts. Chapter 20, we're just going to pick the parts of chapter 20 that are relevant to this discussion. So this video, we're going to say a lot of things without saying why that is. And then chapter 20 will explain some of the things that some of the facts that we just bring up in this video. Okay, so you'll see this this graph right here. So on the left we have the textbook, and on the right I reproduced that graph. So the motivating example here is looking at these two paths on a PV diagram. So we have the same initial point for both of these paths, and we have different final points, but we have the same final temperature. So notice how the two final points are on the same isotherm. So path A is a constant volume process, path B is a constant pressure process, and we want to be able to answer two questions. So the first qualitative one is just which is bigger, QA or QB. And the second question is a bit more quantitative. So assuming the gas is helium and assuming that QA is 30 joules, what is QB? So that actually gives us enough information to see how many joules QB is. Okay, so part A. So to see what's going on, so to see the relationship between QA and QB, what we can do is just use the fact first that we have delta E thermal is the same for both. So delta E thermal for path A is equal to delta E thermal for path B. And notice how they're positive for both of them, because so delta T is positive for both, that means delta E thermal is positive for both. We'll use that fact later. Okay, so then using the first law of thermodynamics, we can replace each of these with heat minus the work done by the gas. So I'll put W by for path A, and I'll put minus W by for path B. Okay. Now, path A is very special. It's a constant volume process, so work done by the gas in path A is 0. So this is 0 just because it's an isochoric process. So if you integrate that, there's obviously no area underneath path A. So we have QA is equal to QB minus the work done by the path, by path B, by the gas in path B. And notice how that's positive. So the work done by a gas is the area underneath the curve, and the area underneath the curve, because we're integrating from left to right, is going to be positive. So QA is QB minus a positive number. Remember, we said that this is positive. Remember, delta E thermal is positive because delta T is positive. So we also have, so we know QA is positive. So QB is something minus a positive number equals still a positive number. So this is an even bigger positive number. That's not POS. That's not the abbreviation. It's positive. So QB is bigger than QA. And they're both positive. Okay. QB is bigger. We've answered part A, which is larger, QA or QB. So even though the change in temperature is the same for both of these paths, one involves more heat transfer, more energy in the form of heat is involved in path B. And the reason for that is that the gas does work. So you give energy to a gas in the form of heat, and the gas, if the gas is allowed to expand, it's getting rid of some of that energy, right? It needs energy. It gets rid of energy because it takes work by the system to push on its surroundings to expand. So you're giving it some, so you need to give it even more energy because it's going to lose some of that energy in expansion. Whereas for path A, all the energy that you give it goes to heating up the material. That's why it needs less energy there. Okay, now for part B, we need to take an aside and talk about, whoa. How do I get back to colors? There we go. What the heck? These colors. It's driving me nuts. There we go. Sorry about that. Okay, so for part B, we need to take a little aside here. So first I want to focus on some of these formulas right here. Okay, so quantitatively. So quantitatively, let me just write down some results here. So the heat added to a gas in an isochoric process is NCV delta T. Okay, but Q for isobaric is equal to NCP delta T. So you can probably guess what the V and the P are. This is constant volume and constant pressure. So maybe actually let's just put constant V here and constant P here. And you'll see exactly what those subscripts are for. Okay, now the book goes into more detail about this, but these two coefficients, CV and CP, are related. So we already saw that if delta T is positive, both these Q's are positive. And we just saw that a constant pressure process has a bigger Q than a constant volume process. So we know CP is bigger than CV. And it turns out that the difference between the two is exactly the same no matter what. So notice in this table here, CP minus CV looks like that's the ideal gas constant, R. CP is equal to CV plus R. Okay, so these are some key equations right off the bat. So Q is proportional to delta T for these two processes, but be careful because in other processes, so we're gonna look at isothermal processes and adiabatic ones, and for those two, it's not true that Q is proportional to delta T. So for horizontal lines and vertical lines on a PV diagram, there is an equation like this where Q is proportional to delta T, but not for every process. So be careful. Okay, so in terms of the actual value of CP and CV, so notice how these are. Okay, so this was introduced in the previous section. C's, the capital C, is a molar heat capacity. So just like we had specific heat, we have this is very similar, except we use a capital C to indicate that it's per mole rather than per kilogram or per gram. So if you multiply by the number of moles and you multiply by a certain number of Kelvin, you'll get joules out. So the SI units here are joules per mole Kelvin. So something that has joules per mole Kelvin is the ideal gas constant too. So notice how these are the same dimensions. So CP is the molar heat capacity at constant pressure, and CV is the molar heat capacity at constant volume. Remember, the subscript is saying which quantity we're holding constant. Right. Now, the actual value of CP or CV depends on what kind of gas you have. So for a monoatomic gas, the value of CV is always 3/2 R. And the value for CP, so once you have one of these two things, you know the other one, because it's just either a plus R or a minus R. So CV, if we know what CV is, then we know CP is CV plus R. So 3/2 plus 1 is 5/2. Looks like this is 5/2 R. Okay, and notice how all of these monoatomic gases, so R is about 8.3. If you multiply by 3/2, it's about 12, a little bit more than 12, and that's exactly what we see for CV. CV is 12.5. And then if you add R to this, add 8.3, we get this value right here, the value for CP. Okay, so your book just kind of says that, you know, we can measure these things and, oh, look, there's a pattern here. It's trying to get you excited about chapter 20. So I'm just giving you a theoretical result, even though we'll hold off on explaining it for chapter 20. Now for diatomic gases, and really anything more complicated, any polyatomic gas, The value of CV depends on temperature. Okay, and therefore CV also depends on temperature. Now, at room temperature, so you'll notice that everything in this table is at T equals 0 degrees C. So it looks like all of the diatomic gases are approximately the same value. So that's not a coincidence. So let me just mention that at room temperature, and your book in this chapter, it just says that diatomic gases have this value for CV. It's 5 halves R. So at room temperature, you can say that a diatomic gas has CV equals 5 halves R. And at room temperature, again, we can just add the ideal gas constant, R, to this. So at room temperature, Cp would be 7 halves R. 5 halves plus R. So see how this Cv for diatomic and this Cp are the same value? And you see in this table how we have 20.8 for the Cp for monoatomic, and then these values are about 20.8, right? There's a little bit of fluctuation there. And then again, you add that ideal gas law constant, and then you get the value of Cp over here. So we're starting to see these trends. But yeah, we're really, so the fact that this depends on temperature, we'll explore this in chapter 20. This is exactly why the part of chapter 20 that we're going to want. We'll explore this in chapter 20. So that's what the whole next video is about. And to spoil the surprise, we need quantum mechanics to explain this. This is the first time in your physics career of learning that you actually need quantum mechanics to explain some phenomenon, which is pretty neat. Okay, so armed with this information, we actually know enough to solve the quantitative part of our previous problem. So we're going to go back to this diagram and see the relationship between QA and QB. Okay, so let's go back to the blue pen for the part B of the original problem. So back to the original problem. Part B. So I'm just going to copy down that we had QA was the isochoric one. This is going to be NCV delta T. And Q for the isobaric path is going to be NCP delta T. Let's go ahead and divide these two equations. So let's do QB divided by QA. QB divided by QA. A lot of this stuff cancels, right? The N and the delta T's cancel. Remember, it's the same delta T because we're jumping onto the same isotherm, jumping from the same initial isotherm to the same final one. And we're talking about the same quantity of gas. So this ratio is going to be the ratio Cp over Cv. And because we're told in the problem that we had helium gas, this is a monoatomic gas, and so we know exactly what the value of Cv and Cp are. It's 3 halves R and 5 halves R. So I can go ahead and plug in. This is 5 halves R, and this is 3 halves R. So this ratio is 5/3. So we're told in the problem statement, if QA is equal to 30 joules, right? That's what that was in the original problem statement. Assuming QA is 30 joules, what is QB? If QA is 30 joules, it looks like QB is 5/3 times that. Then QB is equal to 50 joules. And indeed, it's bigger than QA, just like we reasoned qualitatively before. Remember, we said that QB had to be bigger than QA, just because some of that energy was wasted due to work done by the gas. Okay. So in this chapter, your book will just say, so by the way, Cp and Cv, your book just says that it's always assuming room temperature. So I'm going to hold off until chapter 20 to talk a little bit more about this, to say, you know, what temperatures, what are the values for things other than room temperature. So we'll explore these two numbers and how that can change in the next video. Okay, so Cp and Cv, I suppose I'll just say that in this derivation on the left right here, the way you can prove that Cp is equal to Cv plus R is to look at this diagram And notice for an isobaric process, it's a nice rectangle here. So W by, you can write the area here very nicely. And that's exactly what they exploit right here. So P times delta V, P is constant, so you can write it as delta PV, and then relate it to nRT. And then simplifying a little bit, you can just extract that R out. So if you compare the CP and CV, they're just off by this factor R. So so the proof just comes from the fact that that's a rectangle. The isobaric process is a rectangle, if you want to know the area. Okay, before, so this is an important point right here. So even before thermal process, I want to mention one fact. Not facts, just one fact. An isochoric process is a very special process in that W is 0. So the QA, so Q for an isochoric process is equal to delta E, and delta E is the same for any process that has the same delta T. Remember, E is a function of T alone. So it turns out that delta E for any process, delta E thermal, any process, is equal to NCV delta T. Oops. So if you're talking about Q and delta T, if you want to relate Q and temperature, it's Q equals NCV delta T only for an isochoric process. But thermal energy, so you can use this for any process at all. So we're exploiting the fact that Q is equal to delta E for an isochoric one. So this is a really useful equation to know. And this is one that we're going to revisit and talk about it in another way in chapter 20. So in that isobaric one, so let me just mention one thing. So for example, in our original example, delta E, so QB, remember, plus the work done by the gas in process B was equal to delta E, thermal. So that was 50 joules. Remember, this is delta E for path B. It didn't matter if I put an A there or a B there, but just because this whole, I'm just reminding you that this equation applies to process B. So remember that QB was 50 joules. That's the quantitative bit that we did before. And then the work done by the gas, sorry, this should be a minus sign for the first law. So that's why the subscripts really help in figuring this out. So this is 50 joules minus, turns out this is 20 joules. And the only reason I know this is that the delta E is the same as QA. So even though in this process, this is an isobaric constant pressure process, see the delta E here for an isobaric process is the same as the delta E that an isochoric process has for the same delta T. And that's NCV delta T. So yeah, this will be really useful because you can apply this to any process. This formula is for any process. And that's what's so special about this. That's what's so nice about it. Any process. Okay. Heat depends on path. So we explored that just in terms of the horizontal versus vertical line before. But I want to talk a little bit about isothermal processes. Your book skips over it. It leaves you to derive it. So, but the derivation is pretty easy. So for an isothermal process, delta E thermal is equal to 0. Remember, isothermal is delta T equals 0. And if delta T is equal to 0, then delta E thermal is equal to 0. And this means that Q is equal to the work done by the gas. So Q is equal to integral of P dV. Integral of, for P, we can replace it with nRT over V from some initial volume to some final volume. And the integral of dV over V is log V. So constant temperature is equal to nRT. Remember T is constant, so I can pull that out of the integrand. And integral dV over V is log V final over V initial. Yeah, so very explicitly we see Q is not always proportional to delta T, right? Here T is constant, so delta T is equal to 0, but there is still some heat delivered to the gas. In an isothermal process, you deliver, so the surroundings are delivering heat to the gas if the gas is expanding, and then all that energy is quote unquote wasted to the gas expanding. Right? So energy is going into the gas in the form of heat, and it's leaving the gas in the form of work, and those two exactly cancel one another. So, and that's why delta T is 0. So Q is equal to the work done by the gas, which is this. Okay, so far we have 3 different formulas for Q. Right, we have for constant volume and constant pressure, we have NCV delta T, NCP delta T. For constant temperature, we have nRT log of the ratio of volumes. So the only other thing left to explore is a new type of process that you haven't seen before. These are called adiabatic processes. And these are ones where you can take as the definition, so what does the word adiabatic mean? It means 8Q is equal to 0. The heat, there is no heat transfer into or out of the gas. So this is a totally new process. So let's take a look at what this might look like on a PV diagram. It's nice to compare this process to an isothermal process. So this dotted line is just supposed to symbolize an isotherm. Okay, so I'm going to imagine starting at this point. If I expand the gas at constant temperature, it would fall along the isotherm. But what if I expand the gas in an adiabatic process? What is that? So to give you a sense of what that might look like on a PV diagram, let me hold off on giving you the answer and saying a little bit more about what this kind of process is. So an adiabatic process, basically in real life, it comes about 2 different ways. So basically there's 2 different kinds of clues in problem statements that tell you right away it's an adiabatic process. Of course, if the problem tells you there's no heat exchange, or if they say Q equals 0, then you know right away it's adiabatic. But the 2 more subtle ways of saying that you have an adiabatic process. So first of all, you could say that the gas is thermally insulated. Thermally insulated. Sorry. Okay, so thermally insulated just means there's no heat exchange. So this is just like a fancier way of saying Q equals 0. Right? The second way that you might be hinted in a problem that you have an adiabatic process is that anything that happens very, very quickly. So sometimes the word quickly is thrown in. So we're still assuming, the fact that we're going to draw a path on a PV diagram, we're still assuming that it's a quasi-static process. So equilibrium is established at every point along the path. But it's quick enough that there's no heat exchange. So by quickly we mean there's not enough time for heat exchange. So one example of this, so I gave an example before of like blowing air out of your mouth. So when the gas leaves your, so if you pucker your lips and you blow out, if the gas is expanding and pushing the other gas molecules out of the way, it cools off. So that happens in a matter of tens of milliseconds. That's not enough time for heat transfer, it turns out. That's why the gas feels cooler than if you just go like that. Another example is if you take a piston of gas and you just quickly squeeze it in, that's not enough time for heat exchange either. So the work transfer happens very, very quickly. This could happen in a fraction of a second. But generally, you need a lot more time for the heat to gradually leave or enter the piston. And remember in the last video we talked about heat transfer mechanisms, so we could see roughly how quickly it would take for that heat exchange. I guess the last example is, so this is a science experiment I did in elementary school, so this is dear to my heart. If you take a rubber band and you hold it up next to like your lip, it feels like room temperature. If you expand it really quickly and then hold it up to your lip, it feels cool. So I was always told that this is an example of an adiabatic process. Maybe this is starting to, maybe it's almost like reasoning by analogy there. But the sort of internal energy of the rubber band is helping in this expansion, which is why it's cooling off. Anyway, the point of all these, or I guess, once you realize you have an adiabatic exchange, the delta E thermal is equal to, so Q minus W by, and the Q is 0. So we're going to draw something here on this PV diagram such that if the gas expands, and I'm going to draw my final point to the right of the initial point, we're going to have W by is positive. If the gas expands in an adiabatic process, delta E thermal is negative. The temperature goes down. Okay, so in an adiabatic process, it's steeper than an isothermal process. So this would be, so the arrow, the way I drew it, is an adiabatic expansion. If I drew the arrow the other way, that would be called an adiabatic compression. So it's not a vertical or a horizontal line, these adiabats. So an adiabat is a path that's following an adiabatic process. If this is an isotherm, this is an adiabat. So it's steeper than an isotherm, and if the gas expands, we're going down in temperature. So notice how we're jumping, the final point is on a lower isotherm than the initial point. Right? If the gas expands, it goes down in temperature. If it adiabatically contracts, it increases in temperature. Now, the formula for this, so notice how, see this W, so by the way, to connect this to the book, this is plus W work done on the gas. So your book is calling W the work done on the gas, and W is equal to delta E thermal. And remember this previous formula we wrote down, delta E thermal for any process, including adiabatic, is NCV delta T. So we can combine our equations to see how the book arrived at this, W equals NCV delta T. Okay, so they're using the fact that Q is 0 right there. Okay, so something I want to mention here is that this path right here, so for an adiabatic process along an adiabat, it's not the case that PV is a constant, right? The temperature is not constant, so the product of P times V is not constant. Instead, we have PV to some power is equal to a constant for every point along that path. So for every point along that adiabatic process, if you take the pressure at that point and then V, and then multiply it by V to this number, this gamma is going to be a number, that's going to be a constant for every point along this path. Or another way of saying it is that P1 V1 to the gamma is equal to P2 V2 to the gamma for any 2 points on this path. So like if this is P1, this final point is at P2, the initial point was at V1, and the final point was at V2, then we can relate those 4 quantities using this equation. So notice how this quantity gamma appears in all of these. So gamma is called the specific heat ratio, and it's the ratio of Cp to Cv. So for monoatomic gases, remember for monoatomic we automatically know Cv is 3/2 R and Cp is 5/2 R. So monoatomic gases have gamma is equal to 5/3. For diatomic, gamma can be a bunch of things, and we're going to explore this in chapter 20. Your book gives a value for this, by the way. So at room temperature, gamma for a diatomic gas is going to be that ratio of the values that we gave for room temperature. So remember at room temperature, CV for a diatomic gas was 5 halves R and CP was 7 halves R. So if you put 7 halves R divided by 5 halves R, you get 7/5, or 1.4. So that's where your book got this 1.40. So your book should probably include a warning with that value. So the top value, the value for the monoatomic gas, is always true. This 1.40 for the diatomic gas, that's only true at room temperature. So we're gonna see that value change in chapter 20. So I'm hesitant to just write exactly what the book is right there. Notice how your book talks about or draws these adiabats steeper than the isotherms. So notice their graphs are consistent with this. Your book writes down not only PV to, so PV to the gamma is the one that helps, that it's easiest to remember for me. You can also write it in terms of temperature and volume. So TV to the gamma minus 1 is also constant. Now, if you're wondering why PV to the gamma is constant, your book goes through a proof. So it uses this delta E is NCV delta T for the thermal energy, and then it uses the definition of work. So work is PdV. And it just follows through that logic. So then it's just rewriting it in a nice way, in a way that we can relate it to the adiabatic, the molar heat capacities. And then, so if you're interested in how we got that, take a look at this proof. Okay, so more on this when we talk about chapter 20.